Hello, Professor Simpson here, back with our second video for Chapter 12, Section 2, Entropy. You may remember that in our first video, we focused on the first two learning objectives listed here: define entropy and explain the relationship between entropy and the number of microstates. Here in this second video, we are going to focus on the third learning objective: predict the sign of the entropy change for chemical and physical processes. Okay, so we would, just as a reminder, that a positive change in entropy, delta S, would signify an entropy increase, and a negative delta S would be an entropy decrease. So we are going to focus in here on this section in being able to predict the sign of that change in entropy based on a couple factors. I'm going to skip ahead here in the notes, past what we already covered, okay, and get to factors that influence entropy. So before we get to that, let me just say that we could certainly calculate changes of entropy, as I mentioned in the last video. Delta S is the final minus initial entropy. And we could look up the values for a specific, for different molecules and compounds. And we can do a sum of all the products, the entropy of all the products, minus the entropy of all the reactants. And we'll get to that later in this chapter. But for now, we just want to be able to predict the signs, and we can do that without having to do those calculations. So first of all, factors that influence entropy. So let me start with, we have seen this picture before where we are looking at the particles in a solid, liquid, and gas. We talked about this when we talked about phase changes and how intermolecular forces break and how that allows the particles to have a little more freedom of movement. So if I think about this with respect to entropy, or the amount of disorder or randomness, then a gas would have, of the three states here, a gas would have the greatest amount of entropy, followed by a liquid and then a solid. Okay, so this helps us in our first way to predict whether or not we have an entropy increase or decrease. That if my changes of state occur in a chemical reaction or in a change of state process, then I'm going to focus in on those states, and I can identify whether there was an entropy increase or decrease. So, for example, if we take a look at number one here, if gases are formed from liquids and solids, that would be an increase in entropy. The opposite would be a decrease in entropy. Okay, so as I look at this first reaction and I look at the states, again, focus in on that information provided in the balanced chemical equation, I see here that I have a solid, and then I produce a solid and a gas. So this is an increase in entropy, or I would indicate that the sign of the delta S would be positive. A gas was produced from a solid. If I take a look at the next example, I started with a liquid and my product is a solid. So as I said a moment ago, just the opposite would be a decrease in entropy. So in this case, as I think about the entropy of my three states, solid would have the least amount of entropy, and it was formed from a liquid. So you can see here that this would be a decrease in entropy, and the sign of my delta S, I would predict the sign of my delta S here to be negative. Okay? Sometimes we have solutions and that are formed. We saw this in our dissolution process in an earlier unit. So whether we talk about the ions forming the solid, or in this case, the ions being produced from the solid dissociating into its ions, we could see here, once again, I'm focusing in on the states here. So an increase in entropy would be a solution formed from liquids and solids. So This is aqueous formed from solids, okay? So aqueous solutions are formed from solids. So this would be, in fact, an increase in entropy, or again, result in a positive delta S value. Now, if they're all in the same state, and in this case, in this next example, I have all gases, and so in this case, I cannot differentiate between solid, liquid, and gas, but if I were to produce more moles of gas, that would be an increase in entropy. All right, so an increase in entropy would be more moles of gas as products. Okay, so a decrease in entropy would be more moles of gas as reactants. So if I look at this balanced equation, again, all gases. So now I have to consider the moles of gas on both sides of the arrow. So in the reactants, I have 1 plus 3, I have 4 moles of gas. And in the products, I have 2 moles of gas. So this is a decrease in the moles of gas. So again, this would be a decrease in entropy, or a negative delta S value. The last one we're going to predict in this fashion is with regards to temperature. So an increase in entropy would be would occur if the temperature of a substance increases. So if we think back to our gas laws and those relationships, as the temperature increases, we talked about how the kinetic energy for the particles would increase, or the particles would move around faster and more and with greater freedom. So now that we understand the definition of entropy, randomness, or disorder, if my particles begin moving faster because I've increased the temperature, you would imagine that that would then produce greater disorder or randomness in the particles. So a temperature increase equals an increase in entropy. Finally, there are a couple other factors that we will come across: the type and number of particles that make up a substance. So if I had 2 different particles, say they're both gases, H2 gas versus helium gas, because the hydrogen has more particles, 2 hydrogen atoms in that diatomic, that would have greater entropy than the helium gas. So I would expect greater entropy here. And variations in the type of particles, so a pure substance versus a mixture. So the more different types of substances, which is similar to maybe what we saw in the microstates when I had 4 different types of particles in the box, the more different types of substances or particles would increase the different variations that I would have, and therefore would increase my entropy. So our next task here in working towards prediction of whether a process is spontaneous is to be able to look at a reaction like the ones that I've listed here. So be able to look at a reaction like the ones listed here and predict what the sign of the delta S would be. So delta S, and I'll be a little more specific here. We're talking about delta S of the system, or the particular reaction or process that we're evaluating. So we can do this qualitatively like I've shown here, and this is really our next big step in the process. We'll get an opportunity through some of the homework and classwork to practice this until we get comfortable predicting the sign of the entropy change. So that wraps up section 2 for us on chapter 12. From here, we'll move on to the second and third law of thermodynamics and start to put it all together, our enthalpy and entropy, to predict whether or not a process is spontaneous.